So in today's lesson, we're going to pick up where we left off yesterday. So this will be a continuation of our note on magnetic force on moving charges. So we're going to pick up after our short note on aurora borealis. So let's talk about some key ideas related to magnetic force. So magnetic force in this chapter will have the symbol F subscript capital M. And there are several factors that affect the magnetic force experienced. It's directly proportional to the magnetic field, which has the symbol B, and I'm going to talk about that in a little bit. It's also proportional to the velocity of the moving charge, as well as the charge on that moving particle. So given that, we can write out a proportionality constant. Here it is. Hopefully you can guess what this is going to look like. You can say that the magnetic force is proportional to the magnetic field times the velocity of the moving charge times the charge on that particle. I should note for you that the symbol B for magnetic field is a new one, though you may remember it from last year, and it has units of Teslas, so with a capital T, so Tesla, capital T. Okay, and we can also come up with some equivalent units for the Tesla, and we'll do that in a short time. So as it turns out, you know, the magnetic force is also a function of the angle between the magnetic field and the velocity of the moving charge. You may remember the right-hand rule from last year's physics class. And so the maximum force is experienced when the particle is moving perpendicular to or at a right angle to the field lines. And so the minimum force is when the particle is moving parallel to those field lines. So a couple of ideas here. So you'll remember from your grade 12 function class that the sine of 90 degrees, okay, so we're looking at perpendicular, right, perpendicular 90 degrees. So that you'll remember that the sine of 90 degrees is 1, right? That sine wave is at 1 at 90. The cos of 90 is 0. So we get maximum force when we use the sine function, and 0 when we use the cos function. So that allows us to add in that angle component and say that the magnetic force is proportional to the sine of the angle. All right, so putting all of those components together, we end up with this function here, that the magnetic force is equal to the magnetic field times the velocity of the moving charge times the charge of that particle times the sine of the angle. So let's explore that a little bit more. Here I talked about, let me move this over, the units for B being the Tesla. Well, let's take a look at developing some equivalent units for the Tesla. Go ahead and do that. Pause the video and then come back when you are ready. All right, so if I isolate B in the formula below, I see that I get F divided by V times Q times the sine of theta, which won't have any units. So that tells me that a Tesla is equivalent to a unit per meters per second times a coulomb. So there's an equivalent unit there. I could rearrange this further. I don't really feel like I need to, but there we have it. So this part of the lesson is a little bit tough to do without us being face-to-face, but that's okay. We'll just do the best that we can. If you take your right hand, make sure it's your right hand, and you place it in front of you, we're going to use what's called the right-hand rule to help us determine what the direction of the magnetic force is. So our thumb, if we place our thumb in the direction of the current, which by the way is the same as, you know, the same direction as the velocity as well, and we place our fingers, that is, in the direction of the magnetic field, then the magnetic force will be in the direction that is perpendicular to sort of coming out of your palm, upward. So, if we have, and that's true if we have positive charges. So let's just get this summarized here. So you're going to place your palm upward. If your right thumb is pointing in the direction of motion, so that can either be the current or the velocity, and you have your fingers point in the direction of the magnetic field, then the magnetic force will be upward or sort of coming right out of your palm. Now again, this is true if we're talking about a positive charge. Now, your book describes, how we deal with a negative charge. I'm going to lay this out here, but then we can sort of talk about it. Let me just get rid of some of these little squares here. Your book will say, well, reverse the direction of the charge, so put your thumb in the opposite direction. And that works because negative charge flowing in one direction is equivalent to positive charge flowing in the opposite direction. Personally, I just say for negative charges, we're going to use the left hand rule, right? So if we use our left hand instead, then the same sort of ideas hold true. Our thumb is going to be pointing in the direction of the velocity or the current. Our fingers are going to point in the direction of the magnetic field, and the force will be from our palm outward. So take a minute to jot all of that down, and then we'll carry on with some practice problems. Okay, so we're going to talk next about the trajectory of a charged particle in a magnetic field. So you'll remember that magnetic force is always going to be, the maximum force happens at 90 degrees to the motion of the charged particle. But, the thing is, when we think about force, right, if I were to, let's say, try to push a box across a floor, I know that the maximum force, the force that will increase the speed of my motion, or make that box get pushed across the floor faster, is going to happen if my force is parallel to that direction of motion. But the problem with magnetic fields is that the maximum magnetic force occurs when it's perpendicular to the direction of motion, right? So what that means is that that magnetic force is not going to work to accelerate the charge. It's going to act only to sort of deflect that particle, to change its direction. So, let's write a little bit of that down. There's no component of that force that's acting in the direction of motion of the particle, which means that we can't really do any work on the particle to increase its velocity, right? So, no work done, no change in kinetic energy, it's not moving any faster. So let's take a look at that. Maybe take a minute to pause the video and write a little bit of that down, right? But remember, if my magnetic force is perpendicular to the direction of motion, it's not really going to increase its acceleration at all. So we can sort of view this almost like circular motion. This is going to be part of this discussion. It's going to be a little bit tricky for me to describe for you, but I want you to grab your palm, and I want you to place your thumb, your right hand, by the way, your thumb in the direction of one of the red vectors for velocity. And I want you to point your fingers in the direction of the magnetic field. And what you'll see if you do that is that your force should be pointing inward. You have to sort of contort your hand a little bit, but if you're able to do that, again, magnetic field pointing downward, velocity is your thumb, right? So find a red velocity vector, and you should see that the force, the magnetic force, points towards the center of that circle, no matter where it is that you place your hand or contort it. So, we can describe the motion of a charged particle to exhibit sort of a circular motion, because the magnetic force is always going to be perpendicular to the velocity at all times. Okay, now on to some other conventions in magnetic fields and forces. So if sometimes we'll draw magnetic field lines in 2 dimensions as sort of coming in or out of the page. And so it's going to be really important for you to understand what these symbols mean. And so if you see a circle with a little X or a plus in the middle, that indicates that the field line is directed into the page at a right angle. And if the field line is pointing out of the page at a right angle, it's going to look like this little dot. So one way that we will teach this is to say, well, think about it like an arrow. So if you had like an arrow, I'm thinking like a, one of these arrows with the, whatever you call them, feathers on the back. If the feathers are, if the arrow is going into the page, if you can imagine this arrow pointed inward towards the page, like being shot at the page, then what you would be seeing is the tail end of the arrow, the sort of like feather-like things. And so that's like sort of like the X in this field line symbol. However, if the arrow were coming at you out of the page, what you would see would be the tip of the arrow, right? And so if we see this circle with the dot in it, we're thinking about the arrow coming towards us or out of the page at a right angle. So those are 2 really important symbols for you to make sense of. All right, moving right along. And so what that's going to do, these symbols, what that's going to do is that's going to make the velocity and the magnetic force parallel to the page. So I want you to, grab your right hand for a second here, and remember that your velocity and your magnetic force are perpendicular to each other, but they're also perpendicular to the magnetic field, right? And so if you have your magnetic field, let's imagine that magnetic field coming out of the page, so that would be your fingers pointing towards you. Your thumb extended at 90 degrees to those fingers would be representing the velocity of that particle. And then you would have your force pointing downward. So by having your magnetic force or your magnetic field coming in or out of the page, we're able to better examine the force and the velocity of these charges. So here are some typical pictures describing the direction of magnetic force, the velocity of the moving charge, as well as the magnetic field. All right, so in this case, we're going to look at a positive charge. So positive charge means that you're grabbing your right hand. So in front of you, you're going to have your right hand, and you're going to remember that your fingers are representing the direction of the magnetic field. And in this magnetic field, I can see that the magnetic field should be pointing into the page. I can see these X's, which are representing the tail end of the arrow. So I'm looking at the arrow as it moves away from me. My fingers are going to go into the page. And so then I'm going to position my hand so that my thumb is pointing in the direction of that red velocity vector. And if you do that, your finger should be pointing into the page, your thumb should be pointing to the right, okay, along this red velocity vector. And you should see that your palm should be facing upward, which indicates that the force of this particle would be moving upward. Okay, now, as soon as I see negative charge, then I want to use my left hand. And so I'm going to focus on one of these. I'm going to highlight it so we can look at it really, just so I know what I'm looking at. This one right here, this is what I want to look at. So you're going to grab your left hand, and I can see that my magnetic field again is into the page. So I'm going to point my fingers of my left hand into the screen, right, and directly into the screen. I'm going to use that green velocity vector to remind me that and that's my thumb. My thumb's going to point in that direction. And what you should have is your palm facing downward. And so the red force vector that you see in this diagram should be describing the position where your palm is down, and so the force is downward. Okay, hopefully you were able to work that out. If not, that's okay. We will revisit this tomorrow when we get together. So let's look at a couple of other examples here. Positive versus negative charge, right? So again, this is a case where I have a magnetic field that is pointing into the page. I can see the back end of that arrow there. So I'm going to use my right hand in order to look at this positive charge. I'm going to point my fingers into the page. I'm going to use this vector right here to determine the velocity, the direction of the velocity of that particle. And so I can see that my palm should be upward, which tells me that the trajectory of that charge in the magnetic field will sort of be in this direction. It should go upward, right? And so again, if I look at this negative charge, I'm going to use my left hand, and my left hand still shows that magnetic field going into the board. So my finger should be pointing into the board or into the page. My thumb is in the direction of motion of that particle, and the force, the magnetic force, is described by my palm coming right out of my palm, and your palm should be positioned downward, which shows that this charged particle, negatively charged particle, is going to start moving but then be deflected downward because of that magnetic force. All right, let's see where you are with this idea. Here I have an example on the right of a magnetic field coming out of the board. And again, I know it's coming out of the board because I see these little symbols here that show a dot, and that dot is sort of like the arrow, the tip of the arrow coming at me. So my magnetic field is coming at me. I also see that I have an electron here, which is negatively charged, and it's showing me that I have that electron moving. Okay, in other words, its velocity is directed, I'm going to say, towards the right here. So pause the video. I want you to think about how to draw the impact of the force on the direction of that negatively charged electron. All right, well, let's work this out for ourselves here. So the first thing I'm going to do is I'm going to grab my left hand. And the reason I'm going to grab my left hand is because this is an electron and it's negatively charged, so that means I'm using my left hand. I also am going to say, well, I'm going to direct my fingers out of the board because the magnetic field is coming out of the board, so I'm positioning my fingers towards me, I guess. And then what I'm going to do is I'm going to flip my hand so that my thumb points to the right, because that is the direction of my motion here, right? So when I do that, fingers out, thumb to the right, I can see that my palm should be facing upward. And so my palm facing upward tells me that the force is upward. And so my particle should be sort of deflected in this direction, sort of like that. So hopefully you did okay with that. And if not, we can kind of clarify that and work through that tomorrow. We're going to move on to a question to help consolidate some of these ideas further. All right, so let's take a look at this example. So it reads, an electron accelerates from rest in a horizontally directed electric field through a potential difference of 46 volts. The electron then leaves its electric field, entering a magnetic field of magnitude 0.20 teslas directed into the page. And so you can see over here that there's a depiction of this. And so if it weren't provided, you may want to draw one out for yourself to help you visualize the problem, right? So I can see that I've got the symbols indicating that the magnetic field is going into the page. I also know it's an electron, so it's negatively charged. And so that's going to be part and parcel of my solution. So the first part of this question says, calculate the initial speed of the electron upon entering the magnetic field. So at this point, it hasn't entered the magnetic field, it is leaving its electric field. And so I know in this circumstance that it's going to have any of its, that its change in, oops, I'm having trouble here with my little pen function. Oh, here we go. That the change in electric potential energy is going to be equal to any change that it has in kinetic energy. In other words, any electric potential energies that it has is going to be converted into helping that increase the velocity of that particle. Well, in this question, I'm given that the electric potential difference here is 46 volts, and so I'm going to search out an equation describing the electric potential energy in terms of potential difference. And you'll remember that, delta E is equal to Q delta V. And so that's what I'm going to use. So Q delta V. And in this case, I'm looking at an electron. So the charge on an electron, you'll remember, is equal to 1.6 times 10 to the power of negative 19 coulombs. That, remember Mr. Millikan? And of course, I have my electric potential difference of 46 volts. Now, kinetic energy, of course, we will remember has the formula 1/2 mv squared, or mv squared over 2. So the mass of an electron, I know, and I can look that up in my appendix if I forget. It's 9.11 times 10 to the power of negative 31 kilograms. And that's times v squared over 2. And so if I go ahead and I solve for v, don't forget to square root that, I'll get a velocity of 4.0 times 10 to the power of 6 meters per second, which is pretty darn quick, but sounds about right for an electron. All right, now let's take a look at the second part of this question. All right, so part B of this question says, calculate the magnitude and direction of the magnetic force on the electron. So let's tackle the first part of this, which is the magnitude of the magnetic force. So you'll remember from earlier on in the lesson that I know that the magnetic force is equal to the magnetic field times the velocity of the particle times the charge of the particle times the sine of the angle between them. And in this case, it looks like it's perpendicular. So let's sub in the information that we know here. We know our magnetic field is 0.20 Teslas. We know it has a velocity of 4.0 times 10 to the power of 6 meters per second. We know that because we just figured that out in the last part of the question. And we know it's an electron, so it has a charge of 1.6 times 10 to the power of negative 19 coulombs. And so working all of that out, again, we should probably, just for the sake of emphasis, include sine of 90 degrees, just to emphasize that the force and the field are at 90 degrees to one another. And when I work that out, I'm getting that the magnetic force has a magnitude of 1.3 times 10 to the power of negative 13 newtons. So now what I'm going to do is I want to take a look at the direction of the force. So again, I have an electron here. I'm going to use my right hand rule, but I'm going to use my left hand because it's an electron. I'm going to notice that, again, my magnetic field is into the board, so my fingers are going, which represent the direction of the magnetic field, are going to go into the page. I'm going to position my thumb along this velocity vector showing the initial direction of the particle in that field. And hopefully what you are seeing is you're seeing that your palm is facing downward. And so if I'm using up-down left, right as my directions, I'm going to say that because my palm is facing downward, that the direction of my magnetic force is down. I'm going to indicate that over here as my direction. Finally, I have the last component of this question, which is asking me to calculate the radius of the electron's path. And so, you'll remember that, the magnetic field is causing that force to be deflected. So deflected sort of like that. So there's a circular motion there, right? And so I'm going to use an equation that allows me to relate my magnetic force to centripetal force. I'm going a few units back. So you'll remember that my magnetic force in this case is really just a centripetal force. And my magnetic force I just figured out. It's, it's symbolized by QV, BQV, and sine theta, but of course we can leave that out because we know sine of 90 is 1. And centripetal force has the formula mv squared over 2. So now let's look at what unknowns what do I not have here? The only thing, oops, and I just goofed, so let me just get rid of that. That should be mv squared, not over 2, but over r, which is my unknown in this case. So r is my unknown. So if I go ahead and I substitute all of my knowns into these formulas and rearrange for r, I'm going to get that r is equal to mv squared over bvq, or bqv. Noticing right away that I have two velocity variables here, which allows me to cancel out the velocity in the denominator, and that will give me one resulting velocity, which will simplify the calculation here. So again, I have an electron, so I'm going to use the, oopsies, let me use a different color here. I'm going to use the mass of that electron, which is 9.11 times 10 to the power of negative 31 kilos. I've got my velocity, which I determined in step 1 as 4.0 times 10 to the power of 6. And I'm running out of space, which is why I'm leaving my units out here. My magnetic field in this case was 0.20 Teslas. And my charge is the charge on electron, and that 1.6 times 10 to the negative 19. And so the radius in this case, when I work all of this out, ends up being 1.1 times 10 to the negative 4 meters. And so you can see in questions like this that I've had to, in the first section, use concepts from electric field in order to get a velocity. You can see in the second portion here that I had to use my magnetic force equation as well as my right-hand rule. In this case, I used my left hand because of the negative charge. And then you can see that in this third component of this question, I had to use concepts from circular motion in order to relate my force, my magnetic force, to my centripetal force to solve for an unknown. So lots of pieces here. So here's your homework assignment. I'm going to strongly encourage that you take a look at these homework problems and work through them at your own pace. And also reserve any questions that you have for me. It may also be useful for you to read through the text section in order to clarify components of this lesson that were not 100% clear for you, and then we can discuss tomorrow.